Good afternoon. My name is Ander. I'm a third-year PhD student based at the University of Manchester. It's a pleasure being here presenting part of the work I've been doing in the Neuquien Basin by presenting this short talk called Distribution and Comparison of Transitional Flow Deposits over an exhumed MTD. In nature, there is a continuum spectrum in sediment gravity flows, and their respective deposits cannot be explained solely by deposited from a flow which is fully turbulent or laminar. These flows are named transitional flows, and their deposits are hybrid beds. The rate of flow deceleration and the cohesiveness of the flows are primary controls on the final deposits. On the model on the left side of the screen, the higher momentum of the overriding turbidity current is detached from the basal part of the flow and deposits the clean sand, while the laminar flow deposits above the cogenetic turbidity. The other model on the right focuses in the vertical segregation of the flow, which records progressive development of geological heterogeneity based on the entrainment of cohesive material. In this short presentation, I'll show some phases from a particular architectural element that sits on top of a seismic scale debris, and later I'll compare with some hybrid beds from submarine lobe. This figure shows a 10 kilometers long downslope orientated correlation, with valley flows coming from the right to the left part of your screens. The studied sandstones are only developed in areas where the debris is thinnest. This distribution suggests that they were highly affected by topography created by this debris. These particular sandstones are named foundered sandstones because of the sedimentary loading processes developed during their deposition. These sandstones are characterized by two divisions. The basal division is formed by matrix-rich, very poorly sorted structureless sandstones with abundant mastone clasts distributed randomly. In contrast, the top division is dominated by matrix-poor banded sandstones lacking any mastone clast. The basal divisions are interpreted as deposited from a flow with laminar state, where the sediment is deposited en masse present. In contrast, the overlying banded sandstones are interpreted as the deposits of transitional flows with a reduced flow deceleration, enough to enable the traction responsible for banding. The lack of any fine-grained interval amalgamation surface or grain size break within these two divisions suggests that both phases were formed under the same parental flow, but with different flow state. The front of that flow was likely to be a debris flow, whereas the rear of the flow had a more transitional flow behavior, probably from the entrainment of ambient fluid or reduced clay content. After the deposition of these sandstones, a thin-bedded sandstone package draped the debris due to the high flow efficiency of dilute turbidity currents, which healed and flattened the long wavelength topography of the debris. The lobe is dominated by sandstone beds comprising a massive lower division and an upper division rich in mastone clast. These beds are hybrid event beds, which represents the deposit of transitional flows deposited under high deceleration rates. Both architectural elements comprise phases interpreted as transitional flow deposit. However, they represent different types of flows and origin. The development of the banded upper divisions in the foundered sandstones is the consequence of fluid entrainment promoting a more fluidal state to a previously cohesive sediment gravity flow. In contrast, the hybrid event beds of the lobe represent the transitional flow behavior, which previously might have been a turbidity current. This change in flow state was triggered by the incorporation of clay with cohesive properties. An hypothesis for this different downslope evolution of these flows might be partially controlled by the nature of the substrate. The foundering processes reported in the first sandstones reveal the unconsolidated state of the substrate. The lack of lithification might enable a rapid incorporation and disaggregation of the cohesive clay, triggering a quick change in flow state. In contrast, the angular and well-preserved mudstone clast observed in the hybrid beds reveals a more consolidated substrate, where the breakup of mudstone clast might take longer, being likely to develop a more gradual flow transformation from turbulent into a flow with cohesive properties. So this is it. Thank you very much for listening to my presentation. I will be very happy to answer any questions, and every feedback or comment will be very welcome.